Welcome back. Let's continue with our discussion of how to solve Fuchsian differential equation. And here I have about a regular singular point, and here I have an example, and we have been discussing how to find the first solution, and that involved as a central result the recurrence relation that still has this parameter r as a coefficient, as a parameter in it. So you need to have that. And what I will discuss in this second part of the episode is how to calculate in a straightforward way this coefficient Cn. So that is a nice and attractive alternative from substituting the template back into the differential equation and working your way through a detailed calculation again. But we do have the solution here, so that is nice. So I can show that my new method, that I will discuss in a minute, does render the very same solution. So that's a check. But before we start, I would like to show what would happen if you would just straightforwardly try to apply this recurrence relation that we have here, this one, to the second smallest solution. You know what happens, you get a division by zero, but I want to show it and make an explicit warning because it is all the more important for the method that I will show next. So what would happen if we would substitute r is minus half, so the second root, which is the smallest root, into this expression, we get minus, and then n minus 3.5, an minus 1, and then down here we get n squared. We are expanding this square, so 2 times n times r2, that is minus n, I would get, and then the square of a quarter, and that cancels. So I would get minus n minus 1.5 an, and in the denominator you get n minus 1. Now here I put this lightning symbol underneath this factor in the denominator, because if you get you would get a division by 0 if n is 1. So if by the time that we would try to calculate a1, we get division by 0 for n is 1, and that is exactly the capital N that denotes the difference between the largest and the smallest root, because that in this case is half minus minus half, that is 1. See? So you get a division by 0 for n is 1, so that would fail if you would just go after a solution of this template form and just reuse the recurrence relation and apply it for the smallest root. You get that fails. So that was also observed by Frobenius in 1873, and that was that he came up with these recurrence relations that he noticed it fails for those cases if the roots differ by an integer. And that's a general phenomenon that can be seen from the theory that I outlined in the lectures. That always happens. For n is n, small case n is capital N, and capital N is, by definition, this. The difference of the two roots. If that is an integer, then you get this division by 0. Because if it is an integer, the reason is that this n takes integer values. So you step up n, you start at a0 and then a1, a2. So sooner or later it will meet this value because it is an integer. If this is not an integer, this difference, you will skip it. But if it is an integer, you will hit it. And then you will get this division by 0, and then the method goes bankrupt and it does not render a solution. So that's clear. Now, my warning is, for the method that I will show now, it is even more important to avoid this division by 0, even at all costs. You stay away from that as far as you can. So for the method that I will show now, we do not write, that will start from this recurrence relation for the an, that still has r as a parameter. That was the advice of Frobenius, keep r as a parameter and profit from that. But do not write it in this way, but, and I will show that now. Over here, so I call it R's method, that is my initial, because I did discover this way of doing it myself a few years ago, and so far I've not been able to find anywhere in the literature. So I went back all the textbooks that have been written on this subject, all the way back to the time of Frobenius, and I also had the original paper by Frobenius of 1873. Well, I'm going to discuss now, as I've not been able to find it in any of those sources. So far I call it R's method, which is my method. And as I said, it is based on having the recurrence relation as a function of r. So that is this very one, but as I warned, do not divide by 0, never, stay away from that. So do not divide by this factor in the first place. That was the prefactor of an, that was the factor here, and leave it there. So the recurrence relation is as you get it before that, before dividing by this, and write it like this. So this is kind of an implicit form. Now you still have r as a parameter. That is what I already announced, what we already profited from for the first solution. So I have it here, and then the thing to know is that the coefficients that we are after, the c's, so here's the template for the second solution. That was a times the logarithm of x times the first solution, and then this correction series which has the c's. And the challenge is, the task before us is to calculate the c's. And this is how to do that in a straightforward way. And the key to that is that was discovered by Frobenius. The second solution can be found by taking the derivative of this general series with respect to that parameter r. So Frobenius' invention was keep that r and explore the derivative with respect to r. And that is how he showed that the second solution is of this form. What was not so much explored, and certainly not to the extent that I will show you now, was that that implies that these Cn are related, can be taken as being defined as the derivatives of these coefficients an as a function of r. So you take the derivative with respect to r, and after that substitute the second root. So r is r2 is minus half in this case. That's the key. Now how to do it? Because you don't have A as a function of R. You have a recurrence relation for A as a function of R, as we saw here. But as I told you, do not divide. So you don't even have this. You have a implicit recurrence relation for A is a function of R, and still you are interested in finding these C's, which are the partial derivatives of that A with respect to that R, and after that have R's R2 substituted. Now, that is actually straightforward. We will just do the differentiation implicitly. You have an implicit equation, so you can differentiate implicitly. That's what we are going to do. So that is step 1. I have a full page and the steps are numbered by Roman capitals, so it starts here. This is the hint, what it is all based on. And the first calculation step is here, so we have a copy of the recurrent relation that we already had, and we are going to differentiate it implicitly with respect to R. So here we go. Now, and this is a product, so I have a product factor of R, and here's an of a factor of R. Now the derivative, so I take the derivative of that times that, and the derivative of that times this. Now I first write the second one, the derivative of this with respect to R, and after that R substituted, R2, is Cn. The derivative of this gives Cn times this with R minus half substituted. Now as we saw that cancels the quarter here, and I get n squared minus 2 times n times R minus half, which is minus n. And I pull n out of parentheses, so that is this. So here that is exactly that factor that we had a few minutes ago. Here. We calculated this. There's exactly this coefficient. It is the coefficient of A that An had. And it emerges here because we differentiate with respect to R, but you have the product rule. So if you have the derivative acting here, you have this factor as a prefactor. It was this, but now it ends up here as a prefactor of Cn. So there it is. Now, and that was a product, so I have taken the derivative of that times the prefactor, but I also have to take the derivative of the prefactor, and that is easier. This is a constant, so that becomes, and I write it at the other side, so that is the minus, so I get 2 times n plus R, and then substitute R is minus half, so that is n minus half times that An. So this comes from the product rule, differentiating that product. And then we get at the other side minus this, and that's again a product, so I take the derivative of this, that becomes Cn minus 1, yeah? And then substitute R is minus half, that becomes minus half minus 1 is minus 3 halves, and at n, the minus is just a copy, and then take the derivative of this with respect to R, yeah, that is minus 1, so I get minus 1 times this. So these terms are the derivative of this with respect to R, taking the product rule into account, and then substitute minus half. So that is just implicit differentiation of that recurrence relation of An with respect to R. What do we get? We get the recurrence relation now for Cn. So that is good news. I have a Cn here in terms as a function of Vn minus 1. So that's again a recurrence relations for the C's. So that's good news, but there's also A occurring here. So I need to have A's as well. But mind you, that is the A that is associated with the second root. And we don't have those yet, because we did calculate A before the break, but those were the A's associated with the largest root, and those were used in A and Y1, the first solution. But these have to be calculated separately So that is the second step, how to calculate those a's, these a's that are associated with the second root. Well, we just used the recurrence relation again, but now substitute r's minus half. So the same recurrence relation, but substitute r's minus half. So now this again, we have already done that. This vector with minus half substituted was this, so that appears here again. But if you just don't remember that, just calculate it. This step is just a matter of calculating the second root into the recurrence relation. What do you get? The recurrence relations for the a only. See, so now the page splits in two halves. I have two recurrence relations actually, one for the c's and one for the a's. Now, so what you can do now is just start. This only involves the a's that you will need, so you can just calculate a few and fill up the left hand of the page with subsequent values of a. So a0, a1, a2. And then you will know the a's that you will need in the right hand side of the page. And you can calculate all the cn. So it's very nice that this kind of it fits together like a gear wheel, like a machine, because it goes back and forth to calculate. You want to calculate C's. For those you need a few A's, and then this step works, produces those A's that you need. It feeds back in here, and hence you go back and forth. That is how the machinery works. That's very nice. A few things that you need to know from the lectures. Then you have to study the lectures and the theory. Then I explain why for this machine to work you have to start from the value a0 is 0. So that is very different from the previous solution, the y1, then a0 is the free parameter. In this case, for the y2, in this case you have to choose a0 is 0. Oftentimes you can see it from the calculation itself, not always, but the theory says you have to choose this a0 equal to 0, otherwise the risk is that what you get is not a solution. But this is at least a sufficient condition for what you produce here will be a solution. So to set a0 to 0, and then you can have your way and start producing the values of a from this recurrence relation except the a capital N. And that happens here, as we saw, capital N, the difference of the two roots is 1. So a1, as you see, is free, because this prefactor is again that vector that gives 0, that threatened to give the division by 0. So a1 is free. You look at an equation here, and you see here indeed that I said you should set a0 to 0, and otherwise you would have found it here in this case, because this equation tells you that a0 must be 0 here. But that is not the general rule. It is okay. Now what about this a1? Well, let's proceed here. If I substitute n is 1 here in order to calculate the c1, you see that again the c1 here has the same prefactor as the a1 here, so that is again 0, so c1 is also free here, but a1 occurs as well. So that is always the case, that this equation, if n is capital N, 1 in this case, then the equations for the c produce the value of the a, n1. And you get it here, see? C0 on the other hand is the free parameter. There has to be one free parameter in that second solution, because we have a second order differential equation, so you will need two. You do expect and you will get two constants of integration. And for that you can choose C0. So you can leave it free or set it to 1 and multiply by a constant afterwards. So usually the calculation is a bit easier if you set it to a value. So I set it equal to 1 here. And then substitute n is 1 into the general recurrence relation to derive an equation. Now, this gives 0. C1 occurs here, but it is free, as I announced. A1 occurs here. 1 minus 2 is minus 1. 1.5 minus 1 is a half times C0 minus A0. See? Now A0 has to be set to 0, so we know that. C0 is free, or you set it equal to 1. This is free, but this left hand side is 0. So you get the result A1 is half. And I've made a note here that A1 is a capital N. Next thing to know, this AN is exactly that coefficient A in the template. That is here. So my left index finger here is calculating the template here for the Y2. That mysterious coefficient A that we have to calculate is always equal to this AN. And we have it. It's half. It's not 0, it might be 0. That might turn out to be 0 at this stage. As you see, you get an equation for A1, so it might turn out the value 0. But it doesn't, it's half in this case. So we have it. Next thing that you have to know. So first thing is this. Cn is the derivative of A with respect to R. And then substitute the second root. Second thing that you have to know, start from A0 is 0. Third thing you have to know is AN appears from the equation for C for n is n, and that is the coefficient of the y1 logarithm term. And after that, the machine runs smoothly, because after this nothing special will happen again. It is just a matter of you have recurrence relations for the C's that will tell you which A's you need, and those A's you can get from the recurrence relation at the left hand side of the page for the A's. And that will no longer produce any difficulties. The special point is the point where the n index, the small index, is equal to that capital N, which is the difference of the roots. And then some things happen, a lot of things happen. You get the AN from the equation for the C's. You need it in the left column to produce all the other A's. And it is the coefficient for the logarithmic term. Over there. And after that, things run smoothly and you work your way out. So here I've done the n is 2, substituted in the recurrence relations for the C, so you get an equation for the C2, because it's 2 times 1, and here the calculation is now easy. But keep track of what you're doing, so this 1 minus 2 times 4 is minus 3, A2, 1.5 minus 2 is minus a half, C1, A1 we have here, C1 was free. So you can choose it any way that you like. Cn, this is, the C1 is Cn, capital N, is really free. If you keep it free, you will find what we found on the previous page, that is the constant of integration that multiplies the y1. So this method, as many methods, produces the general solution again. So instead of only the y2, if you keep that C1 free, Cn, you get the general solution, and it turns out to be the multiplier, the constant multiplier, the constant of integration of the first solution that you already had or not interested in. So if you know that, you might just skip constructing the first solution in the first place, do only this, and you find the general solution. You find them both. So that is this is an efficient and attractive way to produce the full solution. If you know that, remember, it's not so easy, not so difficult to remember that the Cn is the coefficient for the first solution, the y1. And then you have everything. You only have to do this. Produces the whole thing. And also, if you are not interested in the details of y1, you can set it equal to 0 and then simplify the calculation. See? So I did it. You can check it for yourself. It is in the exercise collection, of course, this note. You can check the details of the calculation, and it does produce exactly the same solution as we found in the first place, in the first page. See? So here we have this minus half. That was the an. Is the coefficient of the logarithmic term. So here's the note. An is the coefficient of the logarithmic term. And if you substitute the values, then I get exactly this. 1696. And don't forget to multiply by x to the power minus half, which is 1 over the square root of x. So, that's it. See? It might appear a bit complicated at first sight, but once you get it, it's very elegant. People get very enthusiastic about it. Once you see how the machinery works and very smoothly produces, going back and forth over the page. That's why I show it this way. So it is numbered the steps by Roman capitals, and I have these arrows that show how it proceeds. It goes back and forth over the page. And if you write it by hand, it would fill the page. Like that's very nice to see how it works like machinery. All right, now I hope this will serve you. And at one time when you start to see how it works and master it, you might enjoy it. Okay, well, thanks for your attention. My pleasure.